Hi, this is Jose Miguel Valdez de Rodriguez from Making Math Easy, and today we're talking about vectors. So, first of all, what is a vector? It's a straight line, it's a quantity with magnitude and direction. So, size and direction. They include velocity, displacement. We'll talk about those in physics, but vectors can be described using components, which indicates their direction in the coordinate plane, the XYZ plane. So we're talking about vectors in three-dimensional space. So the space we interact with, cubes, spheres, donuts, headphones, frying pans, all of those stuff. But we're going to talk about how to express vectors in some three-dimensional space in the form some vector is equal to some constant times one vector plus some constant times another vector plus some other constant times another vector. So it's complicated. It's complicated. Look at the math I did over here. It's complicated. So given that vector A is equal to 1, 1, 0, vector B is 1, 0, 1. Oh, by the way, the magnitude of a vector is expressed with the vector's symbol, encoded in, put it in square brackets. So what happens, this arrow over here is what tells you it's a vector, okay? But anyway, given that vector A is 1, 1, 0, vector B is 1, 0, 1, and vector C is 0, 1, 1, and P is 5, 6, 7. Express vector P in the form P equals X times A plus Y times B plus Z times C, where X, Y, and Z are real numbers. Whew, it's a mouthful to read in one breath. Though, I didn't really try it, but... So what we first want to do is look at the fact. We know that P, so we plug in values in here. 5, 6, 7 is equal to X times 1, 1, 0 plus Y times 1, 0, 1 plus Z times 0, 1, 1. And when you add components, you just add the corresponding coordinates together. It's simple. Turns out, here's a formula book of a bunch of formulas that we will probably cover in math, and they're helpful. So it's this one, operations with components. So A, A2, so A1, A2, A3. So this is one of them that we're going to use, this first one. This second one is similar. It's usually what we'll use when adding a negative vector. We can do this if we want. Like if there's a negative value in the vector, we can just subtract them. I usually like to convert something like this second line into this first line because it's easier. And then this is the second one we're going to use. So that point may seem obvious, and to me it kind of is, but the thing is that this is one of the formulas we're going to use in our problem. Going back to our problem, we can see that from our formula, we should have the components X plus, not X, Y, Z, so X plus Y without a Z, strangely enough, and with an X plus Z with Y plus Z. Now it's kind of weird, and it can be in other forms. Like this one is a bit different, where you had this set of coordinates instead. It can be a bit different, but this one is special. So now, looking at what we have, X plus Y must correspond to the 5, and in fact it does. And it turns out we can now turn this into a handy simultaneous equation. An equation where more than one statement must be true, and you can use that statement to solve for something. So what we'll do, X plus Y is equal to 5. That's one statement. but x plus z must be equal to 6. So y and z must be such numbers that some constant number is equal to 6. But at the same time, y plus z has to equal 7. Now, 5, 6, 7 might sound weird, and either it's just a random selection or it's just me, but now we can do a bit of math with this. We can actually, and it turns out things are quite nice here now. Because we know that we can subtract these two. So this one minus this one to get, well, y minus x is equal to 1. And if you're wondering where the z goes, it disappears because of subtracting something by itself. And as you already know, probably from addition, anything subtracted by itself is always itself. So now what we do is that we take this y minus x and bring it with the x minus y equals 5 and sum these together to get 2y is equal to 6. Aha! Now we have almost isolated y. Now we divide by 2 to get y equals 3. So far we know p is going to be xa plus 3b plus zc. But we still have to figure out z and x. First we'll find x, because that's the most recent step we did. So what we do is that 3 minus x equals 1. I'm plugging it in this one. And then we get x equals 2. So it's p equals 2a plus y. So we can say that p equals 2a plus 3b plus something c. Figuring out that something will be super easy. We can plug into either of these two equations. We'll use y. So we get y plus z is 7. Sorry that my z looks a bit like a 2. So 7 minus 3, we get z is 4. So z is 4, which means that vector p is 2a plus 3b plus 4c. Now, let's just test things and see if we get this. We know that if we sum this up, this must equal 5, 6, 7, if the algebra is true. We can test this value. So, let's test it. So 2 times 1, 1, 0, plus 3 times 1, 0, 1, plus z times 0, 1, 1, has to equal 5, 6, 7. But does it? We get 2 plus 3 plus nothing, which is 5. And we get 2 plus 2. Come on. 2. Oh, 4, sorry. This is a 4. 2 plus 4. Ah, that's better. So that is 6. And finally, well, we get 3 plus 4, which is 7. And if things look familiar to you, they should. Because now we've basically substituted the values we just got in this. We substituted the values we got from of x, y, and z from the algebra. We just plugged them in to these simultaneous equations and confirmed that these values are true. And we've basically confirmed that p is 2a plus 3b plus 4c. Well, that's it for Making Math Easy, and remind you to stay curious in math and science.